Radioisotopes are powerful tools across industry, for testing, monitoring, sterilizing, and even power. Because they emit detectable radiation, they reveal what other methods cannot, without damaging materials. This video surveys key industrial uses and how they work. Common applications include non-destructive testing, thickness and density measurement, tracer studies, sterilization, and power generation. We will look at each in turn. Non-destructive testing, or NDT, lets inspectors see internal flaws without cutting parts open. Gamma radiography works like medical X-rays but penetrates dense metal. Common sources are iridium-192 and cobalt-60, used for pipelines and pressure vessels to detect cracks and corrosion. Aerospace and automotive components are checked to keep failures from happening. NDT keeps complex systems safe without destructive sampling. Manufacturing needs precise control of thickness and density on fast production lines. Beta-emitting gauges measure how much radiation passes through a material in real time. Typical isotopes include strontium-90 and krypton-85. If the material gets too thick, the detector sees less radiation, and the line adjusts instantly. This keeps quality high and reduces waste. Real-time feedback is key to consistent production. Tracer studies track movement inside systems, where you cannot see directly. Small amounts of radioactive tracers reveal flow paths, leaks, and mixing behavior. Common tracers include tritium and sulfur-35. In petrochemical plants and pipelines, tracers help pinpoint leaks and blockages. Environmental and groundwater studies use tracers to map subsurface flow. Tracer data guides repairs and optimizes processes. Gamma sterilization kills microbes without heat or chemicals, ideal for heat-sensitive products. Cobalt-60 is widely used to sterilize syringes, gloves, and packaging. Radiation also supports insect sterilization programs using cesium-137. Sterilized males mate but produce no offspring, reducing pest populations without pesticides. Gamma sterilization ensures food safety and medical device sterility. These processes are validated and controlled carefully. Radioisotopes also power nations. Nuclear fission turns isotopes into heat and electricity. Uranium-235 undergoes fission, releasing large amounts of energy as heat. That heat produces steam that drives turbines to generate electricity. Reactors and accelerators make medical isotopes used in diagnosis and therapy. Technetium-99m and iodine-131 are critical for imaging and treating disease. These isotopes save lives through early detection and targeted therapy. Radiation modifies polymers to improve strength, flexibility, and heat resistance. Cobalt-60 gamma radiation cross-links chains to enhance material properties. This produces durable, medical-grade plastics and high-performance insulation. Nuclear magnetic resonance uses isotopes like carbon-13 to analyze molecules. In pharmaceuticals, NMR confirms purity and structure, for drugs such as aspirin. This ensures quality and efficacy in finished medicines. Radiation monitoring helps optimize processes like sulfuric acid production. Sensors track flow rates and reaction conditions to improve safety and efficiency. Similarly, catalyst behavior in the Haber process is studied with radiation techniques. These studies boost yield, reduce energy use, and support sustainable fertilizer production. Small-scale testing scales up to global industrial benefit. Better catalysts mean cleaner, cheaper production. Across manufacturing, isotope-based gauges provide continuous measurements that humans cannot match. Automated control based on these measurements prevents defects and downtime. Operators get instant, actionable data. Figure 2.42, Tracer Study Schematic. Follow the injected isotope to locate leaks or mixing zones. Figure 2.43, NMR Spectrum for aspirin, showing how isotopic analysis confirms molecular structure. Figure 2.44, Catalyst Monitoring in the Haber process. Radiation techniques inform optimization. These powerful methods are tightly regulated and handled by trained professionals for safety. As technology evolves, radioisotopes continue to drive industrial innovation responsibly. For students and educators, these techniques offer rich study areas, from safety to sustainability.